So before I start the discussion today, I just looked quickly at the assignment. So I've seen 22 submission, and this was a group assignment, and I'm not really expecting to see individual assignments because it's a group assignment of two, and if we have 34, so I'm expecting 17. So please just follow the assignment. If I say group assignment, it means a group assignment. So don't work in individual basis unless you take my permission, okay? And I understand the number in class probably could be 33, so there could be a single student who cannot find a partner and he or she needs to work on their own, and that's why I'm going to allow them to work this way. But please don't select yourself, you know what, I'll do it on my own, I'll do it by myself. You need to work in a group. So I'm going to do that for this time. I'm going to mark the assignment, even it's a group assignment. I'm going to mark it for individuals. However, anytime I say it's a group assignment, please work with a group, within a group. Okay, guys, let me ask you, does anyone have any question from last class? Does anyone have any question from last class? Guys, you're so quiet. No questions so far? Everything is okay? Are you doing well?
No questions yet.
Say it again, sorry.
Why not?
I didn't get you.
Is it how are you doing?
I'm okay.
Well, you were just in the movie theater. What happened to the movie theater?
I thought that I'm gonna see all your pictures in front of me, but it looks like I'm a student and I'm in the middle of the, like in the class.
Oh, I thought we were at a movie. What movie are we watching?
That's not a movie. That's something that's like an option on MS Teams. You go from here, you go to gallery, you go to together mode preview. And I thought when I do that, I'm gonna see all your faces sitting on a chair like front of me, but it didn't happen. It's only myself on one of the chairs.
Thought you were taking us to a movie. That's too
Uh,
bad.
Another hot date.
Calm down now.
Okay. Okay, guys, looks like you're doing okay. I just want to kind of break the ice and get started on today's discussion. So looks like you're doing fine and you have no problem or no question so far in whatever I taught you. So something also I want to mention, guys, I'm hoping that you understand the material are being created on the spot. So for example, maybe I was working 1 hour ago to improve the presentation. Uh, there's not much added to the presentation, but this is the way I would like to present my material. So sometimes I'm insisting to change some colors, and because when I change the color, it has a meaning. Like for example, look at my screen. When I go back and I take the statement in our course, we will always use 400R. I mean that. I mean that when I turn it into red, I mean, hey, pay attention. You need to pay attention to this. So guys, please re-download the same file again. So if you have downloaded this file, which is material properties, please re-download again. And I'm just trying to make a better version of my slides. Okay, now, I think in the last class, I said before we start our design and go into deep into math and equations, it's very important for me to make sure that everyone understand the material that we're using, the mechanical properties of the material we're using. And again, I gave you kind of quick introduction last class, and I said in this class where it's reinforced concrete, so two material, reinforcement and concrete. And I think I had also kind of a quick start on different topics on material properties, but I would like to come back and start from this slide here. So this slide here is simply a tension test or tensile test for rebar. I think you guys, this was probably on your strength of material course where you did the test. And when you apply tension on a piece of steel or rebar, it follows the curve you see on my screen. When you have zero stress, then there is no strain. When you start adding more force, so when you increase the force, the stress will increase. Because remember that how do we estimate the stress? It is the force divided by the cross-section area of the member. So we increase the force, the stress will increase. And when the stress increases, then the strain will increase. The relationship will keep linear, will be a line relationship all the way until a very significant point called the yield point. From the name, the yield, it means the member will be elongated without adding extra force. So I don't have to add any extra force. Under the same force, under the same stress, there will be extra elongation or extra strain. And then the member will go into the failure mode where it starts to nick, like nicking, and simply will fail later on. You know, from this discussion, I want to get into the word yield stress. So the yield stress is a very important point on the curve, and it depends on the grade of the rebar. And when I say grade of rebar, I'm referring to the alloy. It means how much carbon I added to my iron to get, you know, my steel. And we have three grades, and the three grades are 300 and 400 and 500. Those numbers are the yield stress of one grade and is measured in MPa, megapascal. Also, there are two different kind of rebar. One is called regular, and we use letter R to say it's regular, or weldable, we use letter W. In general, guys, welding is so expensive, and we don't do it unless we really need it. And that's why in our class here, we always use regular rebar, and we will always use a 400 grade. So anytime from this point on until I say goodbye in the very last class, the F field is always 400. Okay, now one more mechanical properties of the steel is something called the modulus of elasticity. Modulus of elasticity, or some people they call it Young's modulus. You know, there are so many names, but I'm going to use here modulus of elasticity, and which is very much like a spring constant that you learn somewhere in your physics classes. So the modulus of elasticity is the slope of the line before the rebar yields. And simply because it's the slopes, it means the y over the x. If you guys remember, slope means y over x. So basically, it's the stress over the strain. You can see this in the equation in the middle of my slide where I'm pointing right now. Okay, now how much is the modulus of elasticity of my rebar? The code says in 8.4, 8.5.4.1, 200,000 megapascal. Okay, and because the code says that, we can simply find the amount of strain at the point of yield. Okay, so you can see here a very important number in my course is something called epsilon. Epsilon, and epsilon is a Greek word or Greek letter, sorry. So epsilon sub y, it means rebar strain at yield, as you can see on my slide. How do we estimate this number? Very simple. For a 400 grade, you divide the 400, which is the stress, divided by the E, which is 200,000. It is 0.002. It means 2 per thousand. Very important number. Very important number. Okay. Also, I need to remind you that this is a line equation, and a line equation that goes into the zero, it has no intercept, and just y equal to mx, and same here. So y equal to mx, it means stress equal to E, which is simply, it's the m, and then multiplied by the strain. Now, I need to remind you also that this equation here is the line equation, so it doesn't apply anywhere after the yield. If you guys remember, from zero to the yield is the straight line, and then it goes horizontal roughly, and then it goes in a curve where the member will go to failure. Okay, so this equation here only applies before yield. in the elastic zone. And remember, guys, remember, also this something probably you know from strength of material, that if I'm anywhere before the yield, if I remove the force, what's going to happen? Anybody knows? Show your hands if you know the answer. My question is, if I increase the force, but I'm still before the yield, anywhere before the yield, before the stress is equal to 400, and I remove the force, do you guys what's going to happen? Show your hands if you know the answer, please. Seriously? Okay, Harjut, go ahead.
There will be very like a no strain or very little strain because it's gonna come back to its initial state.
Thank you, sir. I'm feeling better now. I'm feeling better. So Harjut, a couple of marks for you. So yes, true, because we are still in the elastic zone. It's called elastic. It means just like elastic, huh? You leave it, it's gonna go back exactly to where it was before, so no strain. However, if you pass the yield, then there will be permanent elongation. It doesn't go back to where it was before. Okay, perfect. Thank you so much. Now, one thing also I want to mention here is that in our design, we don't use the 400, okay? We don't allow our rebar to go to the 400 just because you guys learn with me, there is something called resistance factor. It's a reduction factor, and we have to multiply our F yield by this factor. So the factor for the rebar is equal to 0.85. I bet you by now with Corwin you learn about a similar phi sub s or phi sub s, which is there is equal to 0.9, which is sometimes confusing. Why it's 0.85 here and there it's 0.9? Because the other one is a structural steel, like HSS and tubes and stuff like that, while here it's a rebar. So we use different reduction factor or resistance factor. Guys, one more thing I want to insist here. We will never, or you will never see in my class the F field by itself. You will never see that. Always the F field will be multiplied by phi sub s. So they will be like a twin, okay? Like a twin in my class, okay? Always, it's going to be phi s multiplied by F field. You will see this in action when we look at equations, okay? Okay, dokie, let's move on. And I don't want to cover this one more time. This is about different kind of steel and which one is more popular or which one will cover most of the application. I kind of edited here, give you some kind of clue of where they are used and what are the good things and about bad things. We also talked about the fabric or the welded wire mesh and where they are used and what are the advantage of using them. We also talked about the fiber reinforcing option, and it's expensive option, but it's kind of very fast because simply you don't have to lay any rebar or even tie them. Okay, just get concrete and then bore it. And remember, you only need rebar only, or you have a construction joint or expansion joint. I think this is where I stopped the last class, and hopefully we didn't waste a lot of time just to wake you up and remind you of what we covered before. So this table, guys, very important. You use this table in my class probably 1,000 times, okay? Unless you are able to remember the number in the table, which is very easy, by the way. So this table, it simply tells you what are the available bar numbers in Canada, and those are metric bars. We in Canada here we go from the tiniest one from 10 m, and it's an interval of 5 millimeters, so 15 m, 20 all the way to 55. I want to mention something about this one. You know, the 55 m. I'm not sure if any one of you have seen a 55 m. This is really a heavy bar, and if you have some experience, anybody went to some sites and have some experience and work with rebar, show your hands, please. Okay, Domenico, let me ask you, okay? You just keep your hands up. Keep your hands up, by the way. Keep your hands up. It's okay. It's not a question, it's just a discussion, so no marks here. So I'm not sure if this is going to change your, put your hand down. I want to ask you guys if if you have been to site, like what is the biggest bar you've seen on the site?
What's the biggest one?
What's the biggest one that you have seen, like the largest diameter you've seen on your site?
Me personally, I haven't seen bigger than 25.
Yep. Great. How about Nicholas?
Same.
Yeah, so exactly what I was trying to say. Those bars, like the 55M, I've seen them not really on site. Probably they will be in bridges, like bridge columns, but not really in normal building. Those are very, very heavy reinforcement. Gord, do you want to say something?
Yeah, I was just gonna say that the largest that I seen was the 40 in the Red Deer bridges there.
See, so even bridges, those are very heavy. I myself, like, we got some samples in our lab at SAIT, and those are like, if you see them, like crazy, crazy big. And by the way, it was just like this piece this big, and it's kind of very heavy. Okay, if you get the 55M. So anyway, I'll go back to my slide, and I bet you the one that you will see probably maximum 30M. Okay, 30M, I guess that's the maximum you will see on a site, work like a site. So anyway, so this table, what does it tell you? It tells you here we go. Here is 10M on the first line, and the cross section area of the 10M is 100, and then the nominal diameter is 11.3. And actually, like I think Jelly asked question last class, and I don't think I answered it right. I don't think so. When I read the notes below this table, probably you will know what is 10M. Like the 10 millimeter is what, which is bar number. So this one is a round off of the nominal diameter of the rebar. Guys, listen, that the rebar is not perfectly circle. Like if you look at the picture to the right, where we can see X and then 2 and 0, and this is the we talked about this one before. The X is the mil and 20 is the bar size. Think about the cross section. Do you think the section is perfectly circular? I think if you have some imagination, you will feel it. If you cut section through the rebar, it will never be circular. So that's why this is just like kind of a round off of the nominal, okay? And also even the diameter, it's called nominal dimension, which is are two asterisks on this column. Simply, it never happens. It's just a number, that kind of equivalent number to if they take the material in 1 meter in one rebar, melted and put it in a perfect like cylindrical shape. So in this case, the diameter will be 11.3. So I apologize if I didn't say the right answer last time. I just never read the notes below this table, but I know how to use the number. That's the thing. Okay. Okay. Anyway. So guys, you can see here it's called the 10M, but the nominal diameter is 11.3. However, the code says according to 3.3.3, the bar diameter for calculations, as you can see below the table, it says except for calculations involving bar area. So if you're not estimating the bar area, okay, anything else, what you do is you can use the diameter D sub B of metric reinforcement may be taken as bar designation, which is simply 10M. So guys, let's agree. So by the way, so when the code says maybe, which we look up my screen, I kind of box this out because I want you guys to understand. When the code says maybe, it means both are correct. Whether you use the nominal diameter or the nominal dimension or the bar number, doesn't matter, both of them are correct. But if the code in some other places say shall, it means it's a must, you have no other option. However, guys, let's agree in my class, and I put this in red in my slide. I said in this design class, let's agree to use bar designation or bar number for all our calculation, because we're not going to estimate the area because the area is known. For 10M, it's 100 millimeter square. For 15M, it's 200 and so on and so forth, which means in my class, you will never find the area of a single bar, okay? So please take a note that always, if you want to use the bar diameter for some calculations, then we use the 10 and 15 and 20, not the 11 and 16 and 19.5. Not because it's wrong, but just an agreement between us. And trust me, this will kind of save you some time because it's easier to use 10 millimeter than use 11.3. This is easier for calculations. Okay, dokie. Let's move on to this table. I'm not going to spend any time. This is the rebar in the States because some of you may work in the States or sometimes you get some shipment from the state and you need to understand what does it mean if I say number 3. Number 3 means 3/8 of an inch, which 9 point something millimeter. Okay, now I guess this is the brand new part. We never came to this point here last class. So this, guys, this is the same discussion, but it's kind of we reverse the force. So instead of applying tension on a piece of rebar, we apply compression on a cylinder or cubicle of concrete. Okay, so you can see this machine is not new. You guys, luckily, you had some time to go to the lab and you did your concrete class in lab, not online. So you've seen this yourself. We have 2 machines at SAIT. One which is very, very similar to this picture. And this machine will record both the force, the stress and the strain. The stress and strain. And we have another machine that only measure the stress, which is the force. Okay, not exactly the force is not the stress, but I'm saying if you measure the force, then if you divide by the cross-section area, you will find the stress. But the other machine, number 2, it doesn't measure any strain. It just breaks the cubes and then find the F prime C. Okay, now I wanna just remind you that almost same deal like steel. You have 0 stress, you have 0 strain. As you increase the stress, there is increase in the strain until it breaks. However, the relationship is not really linear. You know, concrete is not like steel. You will get some sort of parabolic shape, a parabola between the 0 and the failure. And you can see this clearly from my screen. Okay, now if we reverse the process from compression to tension, hopefully you notice what happens. So the concrete is fantastic in compression. It takes a lot of force. While you reverse the force from compression to tension, then it takes very, very little. We'll talk about this one shortly. But really what I want you to take from this picture is there are few elements or mechanical properties that you need to understand. Number 1 is your F prime C, concrete compressive strength. And you can see in my text, I said it's the most important mechanical properties, and all other mechanical properties are related to it, all of them. So, which is, by the way, this is fantastic. This is fantastic news because simply if all the mechanical properties of concrete is related to the F prime C, it means I don't have to test them. As soon as I know that is the F prime C is 25 MPa, I can simply find all other properties of your concrete. When I say properties, I'm referring to the mechanical properties. Okay. Next is F sub R. F sub R, it is called modulus of rupture. Modulus of rupture. When I know the name is not really very clear, but modulus of rupture is how much concrete can resist in tension. Okay, which is on the picture you see. Look at the diagram. So if I reverse the force from compression to tension, you can see it goes from 0 to point A. I'm not sure if you can see point A on the curve. Okay, not from 0 to point B. Point B is on compression and point A is in tension. You can see my concrete will crack and fail at very, very low amount of stress. How much is that? That's called F sub R, modulus of rupture, and also in MPa. Next is modulus of elasticity. And since we have 2 material, I'm going to call this one E sub C, not E sub S. E sub S is for steel and E sub C is for concrete. Modulus of elasticity, which is in this case, because it's not really a straight line, and mathematically, because it's not straight line, how can I find E? Simply, it is the tangent to the parabola at 0. Okay, and that's how we find the E sub C, modulus of elasticity. Okay. Finally, guys, when you look at also the curve, at point B, which is the failure, then the maximum strain at this point, very important number in my course called the epsilon sub C maximum strain in concrete at failure. Okay, this number, guys, if you read the code or if you read the literature, you will see it's not really a good, like a one number. It's a range, and it depends on so many factors. Depends on how the concrete is cured, the amount of cement, and so on and so forth. However, in our design, we will need a number, a single number, and the code has specified this number for us. The number is 0.0035, and remember, this number is a strain, and the strain is unitless. The strain is unitless. Okay, now, same as I said for the rebar, there is something called the phi sub S for rebar. There is something here, something called phi sub C. Okay, phi sub C, which is concrete resistance factor. How much? It is 0.65. So every time I use concrete of FC dash, what you do is you never assume that stress arrives to the FC dash, because you're scared that your concrete something happen and you don't get the FC dash. Instead, what we do is we always replace the FC dash by same FC dash multiplied by phi C. And this is a reduction. Guys, if you want, go ahead and multiply, for example, 25 MBA, multiply it by 0.65, and you will get a number. Maybe, I don't know, I don't know, maybe it's 18. So instead of saying my concrete is going to fail at 25 MBA, we're going to say it's going to fail at 18, which is the product of phi sub C 0.65 multiplied by 25, which is FC dash. Okay, are you guys following so far? I need to hear some noise.
Yes.
Okay, dokie, thank you. Anybody else? Just one?
We're listening.
Okay, sir, thank you. Okay, now, so guys, as I said a minute ago, I said the good news is all the mechanical properties of the concrete is related to the FC dash, related to it. So which means if I get concrete FC dash and I know how it performs in compression, right away I know how much it can take in tension and all the other mechanical properties. So I'm going to start here with the modulus of rupture, and this is coming from the code on item 8.6.4, and it's called modulus of rupture of concrete. And the code provides a very simple equation. Okay, the equation is 8.3 on my slide, and it says 0.6 multiplied by lambda multiplied by the square root of F prime C. So I know some of you will say, okay, you know what, everything's clear except lambda. So what's lambda? Lambda, it's just below on item 8.6.5, modification factors for concrete density. You guys know from last year, if you attended my class or other classes, doesn't matter, 7222, you know that concrete comes in, and it can be different density, high density, medium density, normal density or low density. And in that class, and which is not my business right now, you learn how to make it very like high density or maybe normal or maybe low density. And I think there are some people did some research on that in my class. But take a note, please, that in our class, we always use normal density. So when we make a structure concrete that goes into a beam or column or those things, we make it normal density. And density, if you guys remember, the density will be somewhere between 18.5 kilo Newton per cubic meter and 23.6 kilo Newton per cubic meter. Okay. So anyway, in my class, I'm gonna make your life easy. It is going to be always normal density. If it's normal density, you can see that lambda is equal to 1. So my equation is very simple: 0.6 times square root of FC dash. Let me ask you, how about if I use 25 MBA concrete? Okay, what will be the F sub R? Anybody who is good at math to tell me right away how much is going to be the F sub R? That's easy, huh? Okay. Okay. The square root of 25 is 5, and you take 5 multiplied by 0.6. This is going to be 3 MPa, which means, guys, we know if I have concrete of grade 25 MPa, in tension is going to take only 3. Can you guess? 25 and 3. So now we know, concrete is really good in compression, not really as great in tension. And by the way, there is some rule of thumb. The rule of thumb is typically F sub R is going to be about 8 to 15% of your FC dash. 8 to 15% of your FC dash. Okay. And some people, in different literature, people, they say 10%, 10%, 10%. It means 25. It means the tension will be 2.5 only. Now, I know some of you will say, Tahir, we know concrete is good in compression. So are we really, in our design, are we going to consider the tensile resistance of concrete? This is another thing you need to understand. The answer is no. So in my class here, in all my design, I'm going to completely ignore the strength of concrete in tension. I'm going to use concrete in compression only. Okay? So which means from this point on until the end of our classes, what happens is when you look at concrete in tension, I'm just gonna kind of erase it as if it doesn't exist. Okay, now. So why people, they try to understand in that concrete performance and tension, while I said a minute ago that in my class here, for any structural design, we are going to ignore the concrete tensile resistance. You need to read the statement number 2 on my slide. I'm going to read it for you. Concrete tensile resistance is considered for the design of a slab on grade. Now, let me ask you, slab on grade is a word I probably you've seen or you heard about this word in our program. Anybody can give me an example or two of slab on grade? And please show your hands if you know the answer. Okay, we have Gord.
An example of a slab on grade would be like warehouse buildings and such.
Yes, sir. Thank you. Good. Okay. Anybody else can add 2 more examples to Gord? So Gord said, if you go to Superstore, for example, the one you walk in Superstore warehouse, or IKEA or Costco, all those are slab on grade. Okay, let's see, Nico.
Like basement floors.
For sure. Thank you so much. Thank you. That's correct. So, Nico, couple of marks for you. Okay, that's true. In every house, guys, our basement, the floor is a slab on grade. Okay, Marin.
That was, I was saying, like basement of most of the concrete building.
Okay, no problem. No problem. Thank you. Let's see, Nicholas.
Garage and carports.
Thank you, sir. Nicholas. Okay, couple of marks for you here. Okay, let's go with the Toy.
About driveway.
Thank you, sir. Toy. Okay, couple of marks for you. Okay, last but not least, Martin.
Any like sidewalks?
Thank you, sir. That's really a good example. I kind of totally forget about it. But you're right, sidewalks are slab on grade. So guys, what's slab on grade? If you look at the name slab on grade, it means slab and there is a soil below the slab all the time. So it has a continuous support. Yes, the soil, it compresses itself, like as you learned from probably Brian, under the load. And that's why it's not really a perfect support that maintain the point at exactly the same point. It deflects. So as you put load on the slab on grade, it deflects a little bit. The thing, guys, why we use, when we do the slab on grade, you can see the moment is so little. And why the moment is so little? Because the slab on grade has almost continuous support. Okay, because we have soil continuous under the slab on grade. And that's why the moments are so low. And that's why the stress is so low. And that's why we can resist the moment by uncracked section. Look at this name, uncracked. It means concrete is intact in both compression and tension. Okay, and I know some of you will say, Tahir, listen, no, stop. In a slab on grade, we still add some rebar. So if you're saying that concrete is good and it's not gonna crack because of the load, why then we're adding some rebar in our slab on grade? The answer is the rebar in the slab on grade, it is not blazed for a structure reason. It is blazed to resist shrinkage, and that's it. Okay. So guys, what I said is already in the slide under statement number 2. Okay, dokie. Now, let's go to the second mechanical properties. So the second mechanical properties is modulus of elasticity. Modulus of elasticity, and under 8.6.2.2, the code is giving you an equation on how to find the modulus of elasticity E sub C, which you can see is not really very friendly equation. I'll give you a few seconds to look at it. It's here. So here is the equation. Not really nice. It's function of FC dash as we expect, and then also the gamma C, where gamma C is simply the concrete density. Okay. So the code says if you wanna find the E sub C and your concrete is normal density, like our case, and your FC dash is between 20 to 40, then you can simplify this equation to the one I highlighted in red here. So this one is easier, huh? Just 4,500 square root FC dash. Okay. Now something also probably you want to take a note. Okay. Anybody, guys? Again, I'll ask you the same question. Anybody has worked in some construction sites? And I'm not sure if I know sometimes you work in a construction site, but you didn't get to understand and know what is the concrete strength. Okay, like how much, like say you're boring a beam or grade a beam like a grade beam today or slab or whatever. Maybe while you are on site, maybe you don't focus so much for what's the strength. But let me ask you, if you have this experience in normal situation, what will be the typical FC dash? Concrete compressive strength. If you are on site, have you ever seen 70 MBA or 60 MBA or 80 MBA? Gord?
It depends on what kind of site you're on, if it's
100%.
residential, commercial, or industrial.
I kind of agree, but even I know commercial, they're kind of more relaxant on strength, and because it's just a house and it's not. I'm not saying it's not very important, but just like the house, residential is sometimes funny. Okay, commercial, they are so strict, and I kind of hear what you're saying. Okay, but
typically for commercial and industrial, I don't think I've seen anything less than 30 MPa.
Okay, great. How about residential?
Well, residential is usually 20 to 25, and then whoever's finishing it or placing it usually waters the hell out of it. So.
Okay, but you already gave us the answer, by the way. That's exactly what I want to say. So you said, Gord, in residential is 20, a little bit. Okay, add it to that, and then in industrial or commercial, you will see more than that. It's a little bit above 30. You agree or disagree?
Agree. Yeah.
Excellent. So here we go. So please write down what I'm going to say right now. In my course, you will never see anything below 20, and you will never see anything before more than 40. Okay. And by the way, that's the normal. Concrete will always, like we do it between 20 and 40. And if you try to make concrete more than 40, which is right now, I know that maybe when you poured some concrete last year, maybe some of you already got more than 40. But that's in the lab, okay? Making concrete more than 40 in work site is super dangerous. I myself will not do any design, and I will never do an assumption more than 40 because when concrete needs more strength, you know what to do, huh? You need to add more cement, you need to add less water, and this will create a huge problem. Maybe you'll have a shrinkage and cracking, And that's why any contractor, he is trying to make concrete more than 40. Oh my God, that's super scary. Okay. So anyway, so really what I want to take from this discussion is in my class, you will see FC dash range between 20 to 40. And what does this mean? It means this condition is applied. And if you want to find the AC in my class, then we use this equation. Also, on the same slide, I gave you this number before, the 0.0035. It's not really Tahir choice. This is the code. So the code under 10.1.3, talking about the maximum concrete strain, which is epsilon C maximum. It is 0.0035, 3.5 per thousand. Okay, very important number. We will use it so many times shortly. Okay, we have a very kind of a topic which I know you've seen this table before. Anybody will go ahead and raise the hand and tell me when did you see this table before? Where did you see this table or when? Rudy, go ahead.
Mixed designing.
Absolutely. So this was so thank you so much, Rudy. Couple of marks for you. So what happened is true, yeah, this table was part of the mix design, because when we design mixes, we simply have to look at the durability requirement, and durability in plain English, it is the long-term performance of concrete. So what happens to my concrete after 5 years, 10 years under exposure to chloride, to cycles of freeze and thaw, or maybe sulfate. And that's why it's very important to understand, and it's not very difficult. The way we do it is we look at this table, which comes from the code from CSA 823.1. I'm not going to spend a whole bunch of time on that because I have other topics to cover, but just quick reminder because I need that. Okay. For example, let's say I'm working on designing a building, and the building has a wall or a grade beam, and the soil, when I looked at the soil report says your soil has a severe amount of sulfate. The soil has a severe amount of sulfate. Guys, as soon as you hear the word sulfate is not really a friend with concrete. It simply interferes and interacts with concrete and creates kind of a gel, and there will be some cracking, and simply it deteriorates the performance of concrete on the long term. And that's why you have to be very careful. So what do we do is we look at the this table here, and because we got the information that my soil has severe sulfate, then my concrete, which will be in contact or exposed to this kind of soil, must follow and satisfies the requirement for S2 concrete. So the exposure here is S-2. Okay. Then what? What do I do when I know that my concrete has to be S-2? Maybe you don't feel it much for now, but you will see. Here we go. Number one, looks like I need to provide more protection for my rebar. So what happened is, if you have concrete which needs to be or meet the requirement of S2, and it's a grade beam, as we said, it's a beam here. So it means your concrete cover must be 40 millimeters. Look at my row and column. This is how we find the cover. So that's one thing you must do. You must maintain the minimum cover according to the exposure. What else? You have to keep going and look at other tables from the durability table. Look at this, please. So if your concrete is S-2, or it has to be or meet the requirement of S2, then number one, your maximum water cementing material ratio has to be 0.45. It cannot be more than 0.45. In addition to your minimum strength, it has to be minimum of 32 MPa within 56 days. Is that clear? Any questions so far? Are you following? Am I going very fast? Am I going very slow? Am I not going?
No, you're doing good.
Good pace.
We're
Okay,
just-
Good.
okay, thank you, sir. Okay, dokie. So again, my intention not really to teach you in detail durability, because this is something you learn, but I included my slide for your review. So please ensure when you study these slides, you need to understand what do you mean by exposure, and how do we select the concrete cover, and next is what should be the minimum strength and maximum water cementing material ratio depending on the exposure. Okay, perfect. Now we're coming, guys, we're coming very, very close. I know some of you are like bored, but we're coming very, very close to the real business. Okay, now here we go. We have here a beam section. So what you see on the right is a beautiful beam section that I spent some time on my CAD to produce. Okay. Really, I want to get you understand all the elements in the beam. And because again, if we go ahead and teach you the design, you need to understand every single letter on this in this slide. Every single letter, not word, letter. Okay. So guys, you can see a typical beam section, which is you can see I kind of make my border of my beam thick in blue, and I also show you how the beam is attached to my slab. And next is I did kind of anatomy, so I show you the anatomy of the beam. The beam is concrete, yes, but it has some other elements embedded into your concrete. Now let's talk about dimension first. Dimensions, okay? So from this point on, I'm going to call the width of my beam B, huh? Width of my beam, letter B. Now, guys, when it comes to the concrete beams, I know that there are so many shapes of concrete beams, are so many shapes, but the most common one is simply the rectangular section. You can, because concrete, it can take any shape, and applying this concept to beam, column, anything, then beam can be any shape. However, the most common beam shape is rectangular section. Okay, and that's what you will learn in my class. And I bet you 99% of the beams that will be cast in place, like cast on site, will be rectangular. Yes, of course, if it's precast, that's a different animal, different business, and it can be any shape like I or T or double T, and we will talk about those shapes later on. But for now, please understand that in Taher's class, the beam will always be rectangular section. Now the width is I call it B, and you will see on this slide it's minimum of 200 with interval of 50 millimeter. I will run the discussion one more time, the same discussion when I start my design on Monday. But please, for now, think that every time I'm going to talk about beam width is going to be a B. Also, the H here is the overall depth. The H, take a moment, look at that sketch on the right. The H marks the overall depth of your beam. And sometimes we don't say overall, sometimes we say the depth of the beam. That's it. So whether you say depth or overall depth, it means the same thing, which is from the top of the slab, which is top of beam. Huh? Look at this TOS. TOS, do you see that? When you see TOS, it means top of slab. And please, the top of the slab is the top of the beam. So your beam does not start from the underside of your slab. The top of the slab is the top of the beam, where you measure the H all the way to the bottom, the bottom of your beam. That's H. Okay, and again, this is a rounding of an interval of 50 millimeter. So we always build beams 500, 550, 600, 650. So it's 2 inches interval or 50 millimeter. Now there is another kind of depth, and this one you must say this way. It is effective depth, and since it is different, I kind of color it in red. Effective, and the word effective, you will get to understand why do we call it effective. Okay, you will understand this is very, very shortly, but it's not the overall depth or the depth of the beam. It's called effective depth. So what is the effective depth? It is the distance from the centroid of the rebar group to the top of the slab. One more time, the effective depth is the distance from the centroid of the group of rebar to the top of the slab. Okay. Next is area of steel. I'm going to use A sub S for area of steel, and also this sometimes it's confusing in my cross section. How many colors for the rebar you see? How many colors? Are you guys able to see how many colors did I use for the rebar?
3,
Yes.
4.
3 colors. Thank you so much. I used 3 colors, and by the way, that's on purpose. That's for educational purpose. I'm not gonna color them all the same, although all of them, they are still rebar. However, they serve a different function in your beam. Okay. As we finish our course, you will understand the function of each. But for now, the one that is in magenta, which is at the very bottom of your beam. Those are what we call it main reinforcement. Those are the one responsible for resisting the tensile stresses. Okay. And so when I say main reinforcement, I'm referring to the area of the steel of those guys. So when I say AS, it means I'm not including in this AS, not the cyan, not the green. It is only the area or the cross-section area of the pink ones. Okay. Or the magenta ones. Okay. Very clear. Now, next is there is something called rho, and I put it here in my slide, RHO, rho. That's how we pronounce it. Reinforcement ratio. Reinforcement ratio. It is the ratio between steel and concrete. So the area of steel, which again, it doesn't include the green, it doesn't include the cyan, it only includes the pink ones, divided by area of concrete, which is B times D. I know some of you will ask me, why did you replace the AC, which is area of concrete, by B times D, not B times H? This is a discussion. I will come to it when we derive our equation. That's a pure derivation, so please be patient. But for now, when we say reinforcement ratio, it is area of the steel of the pink bars divided by area of concrete, which is B times D, and typically expressed in percentage. And you will get to know more about that today. Okay. So next is there's something called letter small s, which is called the rebar spacing. Rebar spacing, and you can see. I want you guys to look at my screen. Probably I need to zoom in, so I'm gonna zoom in to see better the S. So S is not the center line to center line. S is not the center line to center line, rather than the clear spacing between the rebar. And guys, hopefully you understand why it's important. Why do we need to deal with it? Because simply if this distance is so tight, very small, it doesn't allow concrete to flow in between the rebar, and you will have problems. Okay. And that's why we have to maintain a specific or a minimum distance for S. Again, S is rebar spacing. Next is, you can see it's here, something called C, which is concrete cover. It is from the outside face of concrete to the stirrup. Okay, I'll talk about the stirrup, and probably I'll talk about other elements in this picture here. So I guess we finished everything so far. Let's move on to the rebar. So as I said one more time, those rebar at the very bottom in pink, we call them main reinforcement. So what they do is they resist the tensile stresses due to the bending moment, because concrete cannot do it. Next is the cyan ones. They have a different name. They call skin reinforcement, and they serve a different function, different job in the beam. And then also perpendicular to the, or parallel to the plane, because those are going perpendicular to my picture, perpendicular to my screen, like the pink or the cyan or the green. Those three groups, they go perpendicular to my screen. How about the red, which is stirrup? The stirrup goes parallel to my screen. So the stirrup, it has a function. I'm not going to say it right now. It has a function which we will deal with it later in my course. The top ones, the green ones, they are called stirrup hangers. Stirrup hangers, and I don't think I have to mention their function, because simply their function is the name. They hold the stirrups up, okay, and make a box. That's it, okay? Now, something I wanna also make you take a note. Stirrups are mostly 10M. I bet you, I'm not sure, anybody again has some experience on site, if I ask you, have you ever seen a 15M stirrup? And if you did, how many times? Have you seen a 15M stirrup on site? And if you did, how many times? What's the most common? Please confirm, Gord.
Most common stirrups are 15M on commercial and industrial. Seen
No, sir.
far too many of them.
No, sir. No, sir. I disagree. I've been doing design for years. I disagree. 15M, I'll tell you, and you will see that by numbers, okay? If I cannot convince you, maybe you've seen this in a very heavy like work, because the stirrups, they will carry the shear. So if the shear forces are so high, then in this case we will need 15M. But again,
Yeah, they were for structural concrete to hold up.
I call them like a transfer beam. Transfer beams, beams, those are
No.
very crazy. Huh?
They were for the support for the LNG project up in Prince Rupert. I can't remember how much propane those things held, but it was gross. I know it was like 60 feet across was the supports.
Okay, can I tell you something else which will look funny?
Yeah,
Okay, but don't laugh, huh?
I'll try not to.
Okay, oil and gas, they are rich. Oil and gas, they are rich. They don't care about the, how much, it's going to cost them. Because before that, the gas price was so high, and you guys know all this shit, huh? The welder will take this much, and it's everything in oil and gas is expensive, okay? And so in oil and gas, I have seen some designers, they know that the owner doesn't care. It's not going to make any difference when they put 10M or 15M, so they always go to the maximum. But I'll tell you, this is not required. And if anybody else work in a warehouse or maybe a multi-condo building and would like to share with me what was the size of the stirrup, I will say they will agree to 10M is the norm. In oil and gas, kind of a different animal. Again, they put crazy amount of rebar, crazy amount. Even the design doesn't necessarily require this number, but they just put lots of safety factor.
I don't disagree. It was beyond obnoxious. I'm just glad I didn't have to tie that bar. That was the last one I've seen. Outside that, I've not seen more than 10M.
Yeah, okay, so great. Thank you so much for that input. Probably I like this discussion, and I like you to talk so much, huh? I love this. I don't want to talk by myself. Okay, so Gord, I will just give you 5 marks here. Okay, so put your hands down, please. So let's go back to our slide. As per this discussion, I said here stirrups are mostly 10M, and the skin reinforcement in cyan, those are 15M as per the code. So nobody is going to use 10M as skin reinforcement. Okay, let's see. Now we'll talk about this the spacing, but I think I'm over time, so I need to break. Okay, because it is already almost 2 p.m. So I'm gonna break right now, guys, and I will see you 2:10. So 10 minutes after the hour. But any question before I break? Any question before I break?
What movie are we seeing?
I don't know what you're talking about, Michael. I don't know.
Just kidding. I'm just joking.
I like Disney movies. If you're you know what, I like one not really the movie that I like has to be action movie, but also has to be funny, and the only person can do that to me is Jackie Chan. I know I'm very sad that he is too old right now, and he doesn't I think as many movies as before. But also to me, that's the best movie I can attend. And for sure, Jurassic Park and stuff like that, huh? Anyway, so I'm gonna break, and I will see you guys at 10 minutes after the hour. Thank you.